It all depends on this next year. Yeah, we did that.
All right, yeah. So on Friday we started talking about chain rule.
I started crying in my sleep.
I thought you were doing that beforehand.
I was about to say, just started.
No,
No.
Yeah,
I
we really
cried
did.
myself to sleep and then I started crying in my sleep. Get it right, please.
Oh, it did
There
take
you go. All right. So chain rule was how we take derivatives of composite functions, right? So we said if we define some function like this, f of g of x, then its derivative, I take the derivative of the outermost layer, don't change the inside, then take the derivative of the inside. Right? So, for example, if my original function was x squared plus 7 to the 14th power, what is the derivative of this function?
14. Parenthesis x squared plus 7 to the 13th power times 2x.
Perfect. Right. We're taking the derivative of one layer at a time. Right. So we went over basic problems like this on Friday. Right. So let's expand this idea a little bit now. We can use chain rule with as many layers as we want. Right? And we're going to see problems that have more than 2 layers. So whenever we're doing that, I'll just write it out like this first. We're just taking the derivative of one layer at a time. So if I want to write our notation, right, I could say I've got a 3-layer problem, right? A of B of C of X. Well, the derivative of that, I'm just going to take the derivative one layer at a time. So first, I'm going to take the derivative of the outermost layer, right? So A prime, and then don't change B of C of X. Then multiply that by the derivative of B of C of X. Then times the derivative of C of X. Right, we're just taking the derivative one layer at a time. Now, the place where we would see something like this most often is maybe a trig function. So something like this. If I say like sine squared of x squared. This is actually a 3-layer chain rule problem. Okay, it doesn't really look that complicated right off the bat. Okay, but this is actually a 3-layer problem. Now, when we have trig functions like this, we write the exponents here, which makes it a little bit tricky to see the layers. So whenever we have a trig function raised to a power, when we want to take the derivative, I want you to rewrite it like this. Okay, these two things mean the same thing. Right? I just moved the square outside of the sine function like that. Right? I mean, this is how we generally write it. But if we write it like this, it's going to be a lot easier to see the layers of my function. So if I want to take the derivative of this, h prime of x, my outermost layer is this square. Right? So the first thing I'm going to do is use the power rule. Bring my 2 down. So 2 times sine of x squared. And then I'm going to write it like this just so we can see what's happening. Okay, I'm going to subtract 1 from the exponent. Okay, obviously, if we're raising something to the first power, we don't actually have to write it like that. Okay, but I'm going to write it like that just so that we can see the layers that we're producing here. What's the next layer in this function?
The
The sine. Right? So now I'm going to take the derivative of sine. So times cosine of x squared. And I'm not going to change the inside of that. Okay, so my first layer was the square. Brought the 2 down, subtracted 1 from the exponent, didn't change the sine of x squared. The next layer was the sine, so the derivative of sine is cosine. I'm not changing the inside of that function. Now the third layer then is x squared. Right? So now I need to multiply by the derivative of x squared, which is 2x. So this is an example of a 3-layer chain rule problem. Yeah, I mean, we could just leave it like that. I mean, really, the only thing we could do to clean it up would be to maybe bring this 2x out front and make it 4x times the sine of x squared times the cosine of x squared. That's about all we could do to clean it up. But yeah, I mean, if this is a free response, you can stop right there. Okay with something like that so far? Alright, how about if I give you about secant to the 4th power of 2x plus 7. Find me the derivative of that.
So can we technically just leave it like that?
Yep, you could just stop there.
Is that how it's going to be on Math Excel?
Yeah, you can input it just like that on Math Excel. Yep. Alright, so my first layer was the 4th power. So I brought the 4 down, subtracted 1 from the exponent. Then times the derivative of the next layer, so the derivative of secant is secant tangent. So secant of 2x plus 7 times tangent of 2x plus 7. And then my third layer here was the 2x plus 7. So the derivative of 2x plus 7 is just 2. Right, so again, we could stop there on a free response, but how would we clean this up for a multiple choice answer?
You would move the 2 in front and get an 8.
Yep, so 2 times 4 is 8. Is there anything else I can do to clean this up? I can combine the secants, right? So I would end up with 4 of them, right? So I could have secant to the 4th power of 2x plus 7 times tangent of 2x plus 7. All right, so again, for response, stop there, but make sure that you can get to this next step if this were a multiple choice question. Right? Odds are that it would be presented like this. Right. You okay with those? We want to try another one? How about, let's try one more here. How about something like this? Plus sine squared of 4x to the 3rd power. How about something like this? Oh. Just throwing you in the deep end.
Yes, you can.
So we just want to think about layers here. Start with the outermost layer, work your way in. It will be, yeah. I think this one actually has 4 layers. Right?
Why do you tweak this? Oh, never mind. I see. You can put this.
Yeah, so I just rewrote this like this. Yeah.
Would it be close?
Well, not yet, because here, this first layer,
Yeah.
the second power. So I need to bring that 2 out front first. And then the next layer would be this, yeah.
Oh, still working.
I got it.
So the next layer is everything on the inside of the parentheses, right? So the derivative of 2x is 2. Then the derivative of this part, my outermost layer here, is the square. So I bring the 2 out front and don't change the inside. So I mean, this is really like that, right? That's what I did here. So, layers, right? We want to look at one layer at a time. We had to do power rule twice on this one, right? Bring 3 down, subtract 1 from the exponent. Then, in my next layer, I had to use power rule to take the derivative of sine squared of 4x. Then the next layer was the derivative of sine, and the next layer was the derivative of 4x. Feel okay with something like that? Alright, then let's take this idea and apply it to a few things that we've already done, like tangent lines. Right. So let's say I give you my original function is not just cosine squared of x. And I want you to write the equation of the tangent line at x equals pi over 4. Right, so my original function is cosine squared. And I want you to write the equation of the tangent line to this function at x equals pi over 4. So I got -1 for my slope. If I took the derivative using chain rule, I got -2 times the cosine of x times the sine of x. Then plugging in pi over 4, I got -2 times the square root of 2 over 2 times the square root of 2 over 2, which is just -1. Then we also needed our y value, so I plugged pi over 4 into my original function. So cosine squared of pi over 4 is 1/2. So we would get square root of 2 over 2 squared, which would just be 2 over 4, 1/2. So then plugging all that information into point slope form of a line, we got y minus 1/2 equals -1 times x minus pi over 4. Is that what you guys get? Okay. So, I mean, this isn't anything new. Right? We know how to find the equation of a tangent line. We just need to find the derivative, plug in our value, our x value to get the slope, and plug our x value into the original function to get the y. Right? The new part is just using chain rule to find the derivative. Right? What about something like this?
Oh no. Okay. Let's do this.
Alright, let's, yeah, I'll make it,
Yay! 2, 3, 4, 5.
have to throw some negative values in there, right?
You don't have to.
Alright, so let's use chain rule to find certain derivatives from tables. So let's say we define a function to just be f of g of x, and I want its derivative at x equals 0. So here we need to use our notation to find the derivative, and then plug in values. Actually, is this going to work out?
I don't.
Let me
No.
double check and make sure this is going to work out. No, that doesn't work. These have to be positive.
Yes.
There we go. Yeah, they do have to be positive
Yeah.
for it to work out.
No negatives allowed here.
Hold on.
It would have worked, I thought.
If it works,
I don't think we would have
It was
English, and I'll have my science.
yeah, it would have worked.
Nope.
No, why wouldn't it?
What?
Yeah, I don't think anybody.
Oh, okay.
How do you go?
So hold on. Yeah, this isn't going to work out. So
Why does it say that I still have?
I think I overcomplicated it.
Probably have to
hang on.
And I didn't get the right answer.
I
Hold
think
on.
you
I might have
did.
to change
I
the
did,
these
just
values
not
to
in the right
work
form.
out.
I think I need that paper as well. Let's just test it out. I couldn't.
Yeah, so
I really think you overcomplicated this.
no,
Of course.
Not you.
this has to.
Why is it adding?
Product.
How would you change?
So let's make this.
I just did the product. Because see how it does the 3x? I just did the 3 times. You overcomplicated that, man.
The way that I set it up wasn't going to work out, so I had to change a couple of values in the table. So instead of this being 1 and 2, if it's 0 and 1, it should work out now. Yeah, so is everybody okay to this point? Right, finding the derivative using chain rule, we would get f prime of g of x times g prime of x, then we plug in 0. So now, this part here, the f prime of g of 0, well, I want to go to my table and figure out what g of 0 is. Well, g of 0 is equal to 1. So this part here is just going to become f prime of 1, because g of 0 is equal to 1. So times g prime of 0. So now I can go to my table and say f prime of 1 is equal to 4. And so then g prime of 0 is also 4. Alright.
Shut up, AJ.
I'm done.
So let's have you guys do g of f of x.
Okay.
So find the derivative of g of f of x at x equals 0. So yeah, so from here to here, I evaluated g of 0. So I went to the table and said, well, g of 0 is equal to 1. So this g of 0 just becomes 1. Right. So then we go to the table and evaluate f prime of 1. So then that's just equal to 4.
Oh, is it? Oh. Okay.
F prime at 0.
At 0, yeah.
Yeah. So f of 0, we said was Wait, did I mess something up?
Yeah.
What did I mess up?
There should be a 0. It should equal 0.
I got 12.
I got
That's a
12.
0. Yeah, it's gone.
Wait.
Wait, what?
So f of 0 is 0.
Yeah.
So then this becomes g prime of 0.
What?
Yeah.
I don't.
So that f of 0 is still inside of g prime.
Yeah.
So this f of 0 just becomes 0, which is still inside of g prime. So then I need to evaluate g prime of 0, which is equal to 4. You're okay. Questions? Do we want to try another one?
Yes.
All right. Let me see if this will work out. Well, let's just do Let's say our original function is f of x squared. And let's just keep going at x equals 0.
Okay.
We did need to use chain rule when we took the derivative, though, right? Because my outermost layer was the square function, so I brought my exponent down, didn't change the inside, and subtracted 1 from the exponent. Right? So this is, we don't need to write that first power, obviously, but then times the derivative of the inside, so times f prime of x. Then plugging in 0 for each of those pieces. Well, since f of 0 is just 0, this whole thing ends up equaling 0. Okay with that one? Alright, let's do one more here. About 2 plus g of x to the third power. And say at x equals 0 again.
G prime of 0 is 4, not 5.
Oh, shoot. I looked at 1, didn't I? Oops. That's 4.
Should be 1 or 8.
That's a 1 in parentheses.
Oh,
Feel okay with using notation for chain rule and finding derivatives from tables like that? Alright, one last idea.
7 minutes. Let's go.
Yep, plenty of time. As long as I can make up a decent problem here. Alright, so let's see, how about so let's say this is my f of x. Okay, and this is the point 1, 2, the point 2, 1, and the point 3, 3. Those are exact coordinate points on the graph. And let's say got another function, g of x. That does something like that. Where again, these are exact coordinate points: 1, 1, 2, 2, and 3, 1. We don't know what these functions actually are. We just have the graph where we have a few exact coordinate points. And let's say we're going to define h of x to be the composition of these two functions. Let's say h of x equals f of g of x. Well, better make sure this works out again here. Let's see. So I want you to find the derivative at x equals 1. Okay? So this is actually a really similar problem to the table, to what we just did, except now we're given graphs instead of tables. We can still pick out the exact same information, though, just from a different platform. So if I wanted to find the derivative here, again, it's the same idea. Take the derivative of the outermost layer times the derivative of the inside. And if I want to evaluate this at 1, I guess these should be more line segments. Yeah. So then if I want to plug in 1, f prime of g of 1 times g prime of 1. Yeah, these need to be segments in order for this to work out. So we can evaluate piece by piece, though. So what is g of 1? So this piece here, this just becomes f prime of 1 times g prime of 1. Right? So I guess I should have made these straight lines instead of curved. And so let's say that that's a straight line there. So now how do I get these pieces of information from a graph? It's easy to evaluate the function value from a graph. How would I then get these values from a graph, slopes from the graph? So what does this even mean? F prime of 1. What does that mean? What am I looking for from a graph? Yes, I'm looking for the derivative, which means the slope, right? So I'm looking for the slope at 1. What's the slope of this graph at 1? 0, right? The slope here, if I'm thinking about drawing my tangent line, this would be a horizontal tangent. f prime of 1 is equal to 0. And now, for this, it doesn't matter what g prime of 1 is because we know the answer is just going to be 0. But what would g prime of 1 be here?
1.
1, right? The slope here, if this is a straight line, would just be 1.
No, I
There is a math Excel up. There aren't any graph problems like